What happens when a massive interstellar object defies the fundamental laws of physics right in our own solar system? On July 2023, astronomers detected ʻAitlas, a visitor from beyond our solar system that's doing something impossible. This object, larger than most comets we've ever studied, entered our solar system at twice the speed of any previous interstellar visitor. But here's where it gets terrifying. It's changing course in ways that gravity, solar pressure, and outgassing simply cannot explain. Every known force in astrophysics has been tested, and the math doesn't add up. Something is actively altering its trajectory, and we have no idea what. On the night of July 1st, 2025, the quiet work of astronomers at the ATLAS survey suddenly turned extraordinary. Their telescopes, designed to scan the skies for near-Earth asteroids, locked onto something that immediately stood out from the familiar background of stars and solar system objects. What they had found was not just another comet or asteroid wandering through our neighborhood, but the arrival of the third confirmed interstellar visitor in history, now known as 3IATLAS. To understand the weight of this discovery, we need to remember just how rare interstellar objects are. The solar system has been around for over 4.5 billion years, and yet, in all of human history, only two such objects had ever been detected before: ʻOumuamua in 2017 and 3I Borisov in 2019. ʻOumuamua was a slender, tumbling shard that mystified astronomers with its odd acceleration. Borisov was more familiar in appearance, behaving much like an ordinary comet, but with subtle differences that hinted at its extrasolar origin. Now, in 2025, just as astronomers were wondering whether these were flukes or the beginning of a trend, 3IATLAS streaked into view, and it would prove to be unlike anything seen before. What set it apart immediately was its speed. Most comets in our solar system move at a few dozen kilometers per second when they swing around the sun, but 3IATLAS was clocked at nearly 60 kilometers per second. That's not just fast, that's more than twice the speed of Borisov, and enough velocity to guarantee that once it passes through, it will never return. It is moving too quickly to be captured by the sun's gravity, forever destined to continue its journey back into the dark between the stars. In orbital terms, this kind of motion is described as hyperbolic. It means the object isn't bound to the sun like a planet or a normal comet, but is simply passing through on a straight, slingshot-like path. But even calling it a slingshot doesn't quite capture the picture. Astronomers measured its trajectory and found something truly astonishing: an eccentricity greater than 6. For context, most solar system comets have eccentricities between 0 and 1, with 1 representing a perfect parabola that barely escapes the sun's pull. ʻOumuamua, which shocked astronomers 8 years earlier, had an eccentricity of about 1.2, already enough to prove its interstellar nature. 3IATLAS, by comparison, was on a track so extreme it might as well have been a straight line cutting directly through our system. It was a cosmic bullet tearing across the planetary plane, and nothing about its orbit looked ordinary. This was more than just a curiosity. The size and speed of the object meant that astronomers were witnessing a visitor from deep space that carried with it clues about environments far beyond the sun's reach. Interstellar objects like this are survivors, fragments of other planetary systems, debris flung out by ancient processes around distant stars. Each one is a messenger, carrying chemistry and history that we could never otherwise access. To capture even a sliver of data from such an object is to glimpse another star system's story. And so, as observatories around the world scrambled to confirm the sighting, the excitement built. This was not a faint, almost undetectable speck. Like ʻOumuamua had been, 3IATLAS was larger, brighter, and moving in a way that made it much easier to track. Within hours, telescopes from Hawaii to Chile, from space-based platforms like the James Webb Space Telescope to ground-based giants, like the Very Large Telescope, all turned their gaze toward it. Before we dive in, Hit that subscribe button and turn on notifications. You don't want to miss any updates on the universe's deepest secrets. And if you love exploring hidden mysteries and unexplained discoveries, give this video a like, so we know to keep uncovering them. The discovery instantly raised the stakes. How often do these objects pass through our solar system? How many have slipped by unnoticed because our instruments weren't powerful enough to catch them? With ʻOumuamua and Borisov, it had been tempting to think of them as rare, once-in-a-century occurrences. But the arrival of 3IATLAS only a few years later suggested something very different. Perhaps the galaxy is full of these wanderers, and we are only just beginning to see them. Even in these first days after its detection, scientists knew they were dealing with something unprecedented. A colossal, high-speed interstellar body, larger than anything we had previously observed from beyond the solar system, was now barreling through our cosmic backyard. Its discovery alone was enough to make headlines worldwide. But soon, as astronomers studied it more closely, they realized that 3IATLAS was not just remarkable for its size and speed. It would soon reveal behaviors that broke the rulebook of celestial mechanics itself. When astronomers first calculated the size of 3IATLAS, the numbers were staggering. The object was estimated to measure between 3 and 7 miles across. To put that into perspective, that's not just large by interstellar standards. It's enormous compared to most comets we've ever studied in our own solar system. Think about ʻOumuamua, our first interstellar visitor. It was less than half a kilometer long, tiny, like a shard of rock drifting through space. Even 2I Borisov, the second interstellar traveler, measured only about half a mile wide. Both were remarkable because of their origins, not because of their size. But 3IATLAS? This is an object that rivals the largest comets in our skies. For comparison, Halley's Comet, one of the most famous celestial objects in human history, is about 7 miles across, and Halley's Comet is considered a giant by cometary standards. The fact that an interstellar body of similar proportions is passing through our solar system is extraordinary. It makes ʻOumuamua look like a pebble, and Borisov like a small stone. By contrast, Atlas is a cosmic boulder, a heavyweight contender among wanderers from the stars. Its mass is equally mind-bending. Objects of this size aren't measured in millions of tons, but in billions. Imagine an entire mountain range set loose and flung across interstellar space. That is what astronomers are dealing with here. The sheer inertia of 3IATLAS means that moving it off course, even by a fraction, would require colossal forces. This is why the later discovery of its orbital shift became such a puzzle. For something so massive, the subtle pushes that normally affect comets, like jets of escaping gas or pressure from sunlight, should have been virtually meaningless. Outgassing, the process where trapped ices heat up and burst from a comet's surface as jets of vapor, is powerful enough to nudge smaller comets and even spin them around. We saw this firsthand with the Rosetta mission to Comet 67P, where plumes of gas acted like thrusters on the icy nucleus. But those comets are far lighter than Atlas. For something measuring miles across, those same plumes are like whispers against a freight train. And then there's solar radiation pressure, the steady push of photons from the sun on small dust particles. This pressure is enough to sweep them away, creating the glowing tails that make comets so beautiful in the night sky. On extremely small interstellar fragments, it could even alter their paths. But for 3IATLAS, a massive body billions of tons in weight, radiation pressure is negligible, practically non-existent. It's like trying to move a mountain with the palm of your hand. This immense size also raises questions about its origin. Smaller interstellar fragments can be explained as debris, bits of rock or ice ejected from their home star systems by gravitational encounters or planetary collisions. But a body this large suggests a more violent or dramatic past. Perhaps it was once part of a planetesimal belt around another star, or maybe even a shattered remnant of a failed planet. Whatever the case, 3IATLAS carries with it the geological history of another solar system, locked inside a nucleus as vast as a city. The scale of this object also influences how we observe it. Unlike Oumuamua, which was faint, elusive, and quickly faded from view, Atlas is bright enough to be tracked by observatories across the globe. Its coma and tail are visible, its spectrum measurable, and its mass so large that it commands attention. This is not a fleeting spark in the sky, but a dominant presence, forcing astronomers to study it in detail. And here lies the paradox. For something so immense, so heavy, so seemingly immovable, the expectation was clear. Its trajectory should follow the laws of celestial mechanics almost perfectly. The sun's gravity should dictate its motion, and nothing else should matter. Gas jets, dust release, solar radiation, those are the forces that tweak the paths of lightweight comets. But for Atlas, those forces should barely register. And yet, despite all this, the story of 3IATLAS does not end with predictability. In fact, its very mass makes the next revelation all the more shocking. For soon, astronomers would discover that this colossal interstellar visitor, which should have been unmoved by such subtle nudges, was not following the path they had calculated. Somehow, against the expectations set by its size and scale, Atlas began to drift, breaking the very rulebook of orbital science. From the very beginning, astronomers thought they understood the path of 3IATLAS. The initial orbital models showed what looked like a textbook example of an interstellar trajectory, a clean hyperbola, slicing through the solar system at an eccentricity greater than 6. In simpler terms, this object wasn't just on a slightly open curve like previous interstellar comets. It was moving on a track so extreme that it might as well have been a straight line across space. Nothing in the solar system could capture it. Nothing could slow it down. Once it was gone, it would be gone forever. At first, this matched the expectations perfectly. With its immense speed and size, Atlas should have been the most predictable of objects. Its path would be dictated almost entirely by gravity, by the pull of the sun, the tiny tugs of the planets it passed, and nothing more. For astronomers, this was reassuring. After all, the mathematics of orbital mechanics are among the most solid foundations of modern science. Newton, refined by Einstein, has given us equations that can describe the paths of planets, asteroids, and comets with stunning accuracy. Predicting where Atlas should be at any given moment was supposed to be routine. But then, the discrepancies began to appear. With each new observation, taken night after night by telescopes around the world, the calculated orbit no longer matched reality. The object wasn't exactly where it was supposed to be. At first, the differences were subtle, almost within the margin of error. But as the weeks went on, the deviations grew clear. Atlas was consistently drifting from its predicted path, as though some invisible hand were nudging it off course. For astronomers, this was both thrilling and deeply unsettling. A small comet might shift its orbit because of outgassing, jets, of vapor from beneath the surface acting like tiny rocket engines. But remember, this was not a small comet. At 3 to 7 miles across, Atlas should have been immune to those effects. Its inertia was simply too great. The tiny forces that move smaller bodies should have been swallowed up by its mass, making them effectively meaningless. Yet here it was, deviating in a systematic way. And this was no random wobble, no single event that might be explained by a fragment breaking off or a collision with a piece of space debris. This was steady, consistent, measurable acceleration, away from its predicted course. That made it even stranger. Nature rarely acts with such precision. Outgassing usually produces chaotic movements, short bursts, uneven spins, unpredictable kicks. What Atlas was displaying looked more like a controlled push, a smooth and continuous force applied over time. The implications of this did not escape scientists. It immediately brought to mind the case of Oumuamua in 2017, which also showed an unexplained acceleration. Back then, it had been easier to dismiss. ʻOumuamua was small, flat, and strange, and maybe outgassing had occurred in a way we couldn't directly observe. But Atlas was a different story. It was far larger, far brighter, and under constant observation. If outgassing were responsible, astronomers should have been able to detect the plumes, the jets, or at least some irregularity in its brightness and spin. Yet none of that matched what was happening. As the data accumulated, the questions only grew sharper. What kind of force could be acting on a body this large? Was there something unusual about its structure that allowed it to respond differently to outgassing? Was it hollow, less dense? Then it appeared, perhaps a loose rubble pile barely held together? Or was there something more exotic at play, something we didn't yet understand about interstellar physics? For the scientific community, it was a puzzle that resisted easy answers. For the public, it quickly became a mystery that captured the imagination. After all, when an object from beyond the stars enters our solar system and refuses to obey the rules we expect, the mind naturally drifts to bigger, stranger possibilities. Was this just another comet, behaving in ways we hadn't accounted for? Or could it be something more, something deliberately constructed, something engineered? Whatever the explanation, one fact was now unavoidable. 3IATLAS was not behaving the way nature said it should. It was drifting, smoothly and systematically, away from the orbit that physics demanded. And in that tiny mismatch between prediction and reality lay the possibility of one of the greatest discoveries of the century. As the days turned into weeks, astronomers threw every tool they had at the puzzle of 3IATLAS. Its orbital drift had been confirmed. The data was solid, the measurements precise. Now the question was simple in form, but staggering in consequence. What force was acting on this massive object, pushing it away from the path gravity alone demanded? The first checks were routine. Solar gravity was recalculated to account for the latest positions of the planets, their small but measurable gravitational pulls tugging at Atlas as it passed. But these refinements only shifted the predictions by tiny margin. The deviation remained. Next, astronomers tested the influence of planetary perturbations. Could Jupiter, with its immense gravity, have altered the course? Could Earth or Venus have provided a measurable deflection during Atlas's inward sweep? Once again, the models were run, the gravitational interactions simulated down to fine detail. The result was the same. Nothing explained the steady, continuous drift they were observing. Attention then turned to solar radiation pressure, the steady push of photons streaming outward from the sun. On small dust particles and thin fragments, this pressure can act like a cosmic wind, even pushing some grains into interstellar space. But Atlas is no dust grain. With a bulk spanning miles and a mass measured in billions of tons, radiation pressure was effectively irrelevant. When astronomers ran the numbers, the contribution was negligible, too small by orders of magnitude to explain what they were seeing. That left one final familiar candidate: outgassing. Comets heat as they approach the sun, releasing jets of vapor and dust that act like natural rocket thrusters. We have seen this process alter cometary orbits countless times. In some cases, the thrust can even flip a comet's spin or eject pieces of its surface into space. If Atlas were venting gases strongly enough, maybe, just maybe, it could explain the drift. For a moment, this seemed promising. Observations did indeed detect significant outgassing, plumes of carbon dioxide, traces of water vapor, streams of dust. The jets were real, and they were measurable. But then came the calculation, the hard math of thrust versus mass. And it was here that the entire explanation collapsed. Even if Atlas were venting at its maximum measured rate, the force would still fall far short of what was required to shift an object of its size. Imagine a mountain-sized body gliding through space, and then picture a handful of geysers trying to nudge it sideways. The thrust simply wasn't enough. The math did not add up. This is where the mystery deepened. The deviations weren't chaotic or random, as one might expect from uneven jets blasting at unpredictable intervals. Instead, they were systematic, smooth, almost elegant. The residual accelerations remained after every known force had been accounted for. It was as though some unseen hand was providing a steady push, one that nature's catalog of forces could not explain. For astronomers, this was a profoundly uncomfortable place to be. Science thrives on cause and effect. When a comet shifts, we point to jets of gas. When a planet wobbles, we point to gravitational resonance. But here was an object that defied those explanations. All the usual suspects had been eliminated, and yet the effect was still there, written into the data with quiet certainty. And so, with the standard toolkit exhausted, scientists were forced into new territory. Was 3IATLAS revealing a kind of cometary behavior we had never seen before? Was its composition so alien that it produced forces in ways we didn't yet understand? Or was it hinting at something far stranger, something that might challenge our assumptions about what drifts through interstellar space? Whatever the answer, one fact was clear. The conventional explanations had failed. The mystery of Atlas was not going to be solved by the familiar rules, and the further astronomers probed into its chemical makeup, the stranger the story became. If the orbital anomaly of 3IATLAS raised eyebrows, its chemistry left astronomers utterly astonished. For centuries, comets have been studied as frozen time capsules, relics from the earliest days of planetary systems. Their compositions tend to follow familiar patterns: mixtures of water ice, carbon compounds, dust, and metals. They may vary in detail, but overall, they fit a template shaped by the laws of chemistry and the environments in which they formed. Atlas, however, seemed to defy this template entirely. The James Webb Space Telescope was brought to bear on the object, its instruments capable of dissecting light into the fingerprints of individual molecules. What it revealed shocked even the most cautious researchers. The comet's coma, the glowing cloud of gas surrounding its nucleus, showed a carbon dioxide to water ratio of nearly 8:1. That may sound technical, but in the language of comet science, it is extraordinary. In our solar system, comets usually show ratios closer to 1:1, sometimes skewed toward water, sometimes toward carbon dioxide, but always within a predictable range. Never before had a comet been observed with so much carbon dioxide compared to water. It suggested that 3IATLAS was built in an environment fundamentally different from anything in our solar system, a place where carbon dioxide ice dominated, where water ice was scarce. What kind of star system produces such chemistry? Could it have formed in the outer regions of a cold, carbon-rich disk? Or was it the fragment of a body that had undergone chemical processing unlike anything we have seen? The ratio was so extreme that it implied Atlas might not just be unusual, it might represent a class of interstellar bodies utterly foreign to our own experience. But the surprises didn't stop there. Spectroscopy revealed the presence of nickel in the ejected gases, something already rare enough. But critically, it was nickel without the usual companion element, iron. In cosmic chemistry, nickel and iron are like inseparable twins. They form together in stellar furnaces, bond in planetary cores, and appear side by side in meteorites and comets alike. To find nickel without iron was like finding smoke without fire. It broke the rules of how elements are distributed in space. This discovery immediately raised profound questions. Could the nickel be trapped in unusual mineral structures that excluded iron? Had Atlas been formed in an environment where stellar nucleosynthesis or planetary differentiation produced an abnormal split between the two metals? Or was this, once again, a hint that the object was not simply a natural fragment, but something processed in ways we could not yet understand? There are two anomalies piled up. First the orbit, then the size, now the chemistry. Each discovery made 3IATLAS look less like a comet in the traditional sense, and more like something unprecedented, a cosmic messenger carrying signatures we had never encountered. For planetary scientists, it was a puzzle that refused to stay within the lines. For astrobiologists, it was a tantalizing glimpse into the diversity of materials that might exist around other stars. And for those willing to speculate more boldly, it was one more clue that perhaps interstellar space holds not just random debris, but things deliberately shaped by forces we do not yet comprehend. One thing, however, was undeniable. The chemistry of Atlas set it apart from every comet ever studied. It was not simply strange, it was alien in the truest sense of the word, forged in conditions far beyond the reach of our sun. And as more data poured in, it became increasingly clear that the mysteries of this object were only just beginning. For a while, the leading hope among astronomers was that outgassing could explain the strange drift of 3IATLAS. After all, comets are famous for this process. As sunlight heats their surfaces, buried ices sublimate, transforming directly from solid to gas, and erupt into space as powerful jets. These jets not only create the comet's beautiful tails, but also act like tiny thrusters, pushing against the nucleus and altering its orbit. When scientists measured the outgassing of Atlas, the numbers seemed impressive at first. Instruments detected carbon dioxide escaping at a rate of around 129 kilograms every second, a steady torrent of invisible vapor pouring into space. Alongside it came 6.6 kilograms of water per second, plus a steady shedding of dust, ranging between 6 and 60 kilograms per second. For a human imagination, these numbers are staggering. It's the equivalent of several bathtubs of material being blasted off the comet every single second. But then came the cold truth. Size and mass matter. Atlas is not a small, fragile object. At 3 to 7 miles wide, it is a worldlet, billions of tons of rock and ice bound together. And when you set those outgassing rates against its colossal bulk, the comparison becomes absurd. The jets of vapor and dust, as mighty as they seem, are no more effective than a garden hose trying to push a mountain. The math was merciless. The total thrust generated by the observed gas and dust loss fell orders of magnitude too weak to explain. The measured deviations in its orbit, even if every plume was aligned in exactly the right direction, which they were not, the combined push still wouldn't come close to budging something this massive. This was one of the most damning results. For the conventional explanation, outgassing is messy, irregular, chaotic. It can jolt smaller comets around unpredictably. Yes, but for Atlas, the effect should have been drowned out by its sheer inertia. Instead, the data showed the opposite, a smooth, consistent acceleration, far beyond what those jets could produce. To make matters stranger, astronomers expected that if the jets were playing a significant role, they would see visible signs, flickering brightness as plumes shifted, changes in the object's rotation, or irregularities in the shape of its coma. Yet the observations showed no such chaos. The object remained eerily stable, the deviations in its orbit smooth and steady. The conclusion became unavoidable. The observed outgassing was real, but it wasn't enough. Not nearly enough. Something else was at work. Some hidden factor, some unknown mechanism was driving Atlas off course. This realization marked a turning point. It was no longer just a question of tweaking the math or refining the model. The mystery was deeper. If neither gravity nor radiation nor measured outgassing could explain the force, then what could? Was Atlas made of some exotic material that responded differently to solar heating? Was its structure hollow, allowing internal dynamics we had never seen before? Or was it possible, just possible, that we were seeing something entirely outside the realm of natural cometary behavior? For now, all astronomers could do was admit what the data was telling them. The jets of gas, however spectacular, were too weak. Atlas was moving in defiance of physics as we understood it, and that simple fact was enough to transform it from a fascinating comet into one of the greatest scientific enigmas of the century. The mystery of 3IATLAS didn't arise in a vacuum. Astronomers had seen something eerily similar before. Back in 2017, the world was stunned by the discovery of Oumuamua, the first known interstellar visitor to pass through our solar system. At just a few hundred meters long, Oumuamua was a sliver of rock compared to Atlas's immense bulk, but it too refused to follow the script. As astronomers tracked its trajectory, they noticed something impossible. Oumuamua was accelerating, ever so slightly, as if nudged by an invisible force. The push was tiny, just millimeters per second squared, but it was real, measurable, and persistent. Yet, when scientists searched for an explanation, none fit. There were no visible gas jets, no glowing coma, no tail of dust. Oumuamua looked bone-dry, a tumbling shard of rock slipping quietly through space. The outgassing that should have explained its drift was simply not there. Radiation pressure was considered, but even that stretched the physics to uncomfortable limits. The result was an unsolved riddle, one that sparked intense debate and even speculation about exotic possibilities, like alien engineering. Fast forward to 2025, and now Atlas is showing the same defiance of physics, only on a scale that magnifies the problem. Oumuamua was small enough that a wisp of invisible hydrogen or a faint release of volatile ice might, just barely, have accounted for the anomaly. Atlas, however, is a different beast. With a nucleus 3 to 7 miles wide and a mass in the billions of tons, it is thousands of times heavier than Oumuamua. A force strong enough to move something that massive is not subtle. It should be obvious, and yet it isn't. That's what makes the case of Atlas so unsettling. Oumuamua could be waved away as an oddball, an outlier with peculiar surface, chemistry, or an unusual shape. But Atlas is now the second interstellar visitor to break the rules, echoing the same inexplicable behavior. The pattern is no longer a one-off curiosity, it's a trend. For astronomers, the déjà vu is chilling. If two of the only three interstellar objects ever observed both show unexplained accelerations, then perhaps this is not an exception. It's the norm. What if interstellar visitors routinely behave in ways our models can't explain? What if our rulebook for comets and asteroids is incomplete when applied to material from other star systems? Oumuamua raised the question. Atlas amplifies it. One anomaly could be dismissed. Two in a row demand a deeper reckoning. Faced with a giant object moving in ways the math could not explain, astronomers were forced back to the drawing board. If gravity, sunlight, and outgassing were insufficient, then what else could be at play? Several possibilities emerged, each intriguing, each flawed. The first was fragmentation. Maybe 3IATLAS had suffered a structural failure, an unseen crack opening inside its nucleus, shifting its balance just enough to alter the orbit. If part of its mass had shifted or a hidden slab had broken away, the center of gravity could move slightly, creating the illusion of an external force. It was a tempting idea, but one without evidence. No major breakup was detected. The coma showed no sudden surge in dust or debris that would betray a catastrophic fracture. Atlas appeared stable, intact, and whole. Another possibility was a density anomaly. Perhaps Atlas was not the dense boulder astronomers imagined, but rather a loose rubble pile, a fragile cluster of icy fragments held together by weak gravity. In such a case, even modest jets of gas could have a larger effect, nudging the structure like a cluster of balloons instead of a solid rock. But again, the chemistry fought against this idea. The unusual composition of its coma, the overwhelming carbon dioxide dominance, and the presence of nickel without iron didn't align with the behavior of a fluffy, fragile object. The data suggested something stranger, something more solid, more exotic. And then came the wild card theories. Some scientists, often outside the mainstream, raised the possibility of light sail-like physics. They imagined a thin, broad structure, capable of catching the faint pressure of sunlight like a ship's sail catches the wind. In such a scenario, the deviations in Atlas's path might not be random at all, but a deliberate consequence of its design. The idea echoed earlier discussions of Oumuamua, which some researchers speculated could have been a fragment of alien technology. The notion of an engineered object is not one embraced by most of the scientific community. It runs counter to the conservative principles of astrophysics, where extraordinary claims demand extraordinary evidence. Yet, the fact that such hypotheses are even on the table says something about the depth of the puzzle. When the standard rulebook fails, minds naturally begin to wander into uncharted territory. At present, there is no consensus. Fragmentation lacks evidence. Density anomalies contradict the chemistry. Exotic explanations remain speculation. What astronomers are left with is a mystery hanging in the void, an object that should not move the way it does, drifting through the solar system with an unexplained force pushing it along. And the question lingers, if Atlas is breaking the rules so clearly, what else might be out there, slipping past our instruments, rewriting the laws of motion as we know them? The strange behavior of 3IATLAS is far more than a minor curiosity. It challenges the very foundation of how astronomers understand the motion of objects in space. For decades, scientists have relied on well-established models based on gravity, solar radiation pressure, and outgassing to predict the paths of comets, asteroids, and other small bodies. These models have been reliable for countless objects within our solar system. But Atlas throws a wrench into that rulebook. If a massive interstellar object can defy all established orbital models, then our understanding of how interstellar bodies behave is incomplete. What we thought were predictable laws governing trajectories may not apply universally, especially for objects arriving from other star systems. This realization carries real consequences. It suggests that there may be other, massive objects moving through or near the solar system whose true behavior we fail to recognize. They could be slipping past detection entirely, or they could be observed but misunderstood, with deviations attributed to measurement errors or random chance rather than true anomalies. The implications extend beyond academic interest. Accurate predictions of interstellar object trajectories are critical not only for understanding the origins of these visitors, but also for assessing potential risks, planning future exploration, and refining models of planetary formation in other star systems. If our models are incomplete, we might underestimate the number of interstellar objects passing through the solar system or misinterpret the forces acting on them. Atlas serves as a wake-up call. It underscores the need for better observation, techniques, more advanced telescopes, and deeper theoretical work to account for forces or properties that we currently cannot explain. The fact that such a large, massive object behaves in this anomalous way forces astronomers to acknowledge that our physics-based expectations, while reliable for local solar system objects, may not fully capture the complexities of interstellar travelers. In short, 3IATLAS is not just a scientific curiosity. It is a signal that the universe may hold more surprises than we anticipate, and that our current understanding of interstellar bodies is only the beginning of a far larger and more mysterious story. The discovery of 3IATLAS is not just a one-off event, it marks the beginning of a new chapter in astronomy. In the coming decade, advances in observation technology are poised to revolutionize how we study interstellar visitors. Chief among these is the Vera C. Rubin Observatory, whose 10-year legacy survey of space and time will provide an unprecedented, continuous scan of the sky. Unlike previous generations of telescopes, which caught interstellar objects largely by chance, the Rubin Observatory will systematically detect dozens of interstellar visitors each year. What were once considered rare anomalies, curiosities like Oumuamua and Atlas, will become a regular stream of data, allowing astronomers to analyze patterns, compare chemical compositions, and track unusual orbital behavior on a scale never before possible. Each new object will carry the potential to challenge or even rewrite our understanding of physics, chemistry, and the formation of planetary systems. Some may show strange chemical signatures, unexpected ratios of elements, or acceleration anomalies like ʻATLAS. Others could reveal clues about the environments of distant star systems, or even hint at phenomena we have not yet imagined. ʻATLAS serves as a warning and an invitation. It reminds us that the universe is far stranger than our textbooks suggest, and that interstellar objects may not obey the simple rules we've long relied upon. With upcoming observatories and advanced instruments, humanity is poised to track, study, and understand these cosmic travelers like never before. The next decades promise a flood of discoveries, each interstellar visitor a messenger from distant star systems, carrying insights that could redefine what we know about the galaxy. From chemistry to orbital mechanics, from physical structure to possible exotic phenomena, the universe is about to open its doors in ways we have only just begun to imagine. In short, 3IATLAS is not the end of the story. It is the beginning of an era where interstellar objects become key players in our quest to understand the cosmos, challenging our assumptions and expanding the frontiers of human knowledge. If you found this journey through hidden science, cosmic secrets, and potential alien infrastructure as mind-blowing as we did, make sure to subscribe and hit the notification bell. Don't miss future explorations into the universe's deepest mysteries, because some secrets are just waiting to be uncovered.